Good morning, dear students. Welcome to the course of Mechanical Metallurgy. Before introducing myself, I wish you all a happy and prosperous New Year 2012. Myself, M. Vijayalakshmi, BTech from Andhra University and MTech from IIT Madras in the Department of Metallurgy and Materials Engineering, currently working as an assistant professor in Mahatma Gandhi Institute of Technology. I am pursuing my PhD in the Central University of Hyderabad. So, you can contact me if you have any doubts regarding the subjects. This is my mobile number 9052003346 and to my email ID vijaya all small letters .511@gmail.com. Regarding any clarifications or any doubts, you're free to contact me to my mobile number or you can mail me to my mail ID. Now let's start to the introduction of the subject mechanical metallurgy. Mechanical behavior of solids, mechanical behavior of materials, it deals with how a material responds to the applied forces. This is very important because during the initial fabrication steps, that is like forging, rolling, during the initial fabrication of a cast ingot as well as later part after a component is produced after processing and it is placed in a certain application, then with respect to the applied forces, how it responds is very, very important. Because if the load is very high, the material may undergo excessive plastic deformation or it may also undergo fracture. So to avoid these possibilities, excessive plastic deformation and fracture, you need to know how a material responds to the applied load or what is the effect of the external force or external load on the part. So the main important mechanical properties are the strength, stiffness, hardness and ductility. These are the important mechanical properties that we come across during the course. Strength, important mechanical properties, strength, hardness, stiffness and ductility. The three important loads that are applied to the materials or which the materials encountered during service are tension, compression and shear. The main important loading types are tension, compression and shear. Tension is, if you pull that material, it is simply like stretching the material. When a material is stretched, it undergoes some increase in length and reduction in cross-sectional area. That is tension. Consider a cylindrical rod of cross-sectional area A0, which is the initial cross-sectional area of the cylinder A0, and the length is L0. And if you stretch this cylinder uniaxially, that means you are applying stress or you are loading the cylinder along one direction. So that is uniaxial loading or uniaxial stress. Then this material will undergo an increase in length. the length will increase. Correspondingly, there is a reduction in cross-sectional area. So this will be the final length of that material, L, and the final cross-sectional area is A. So this is an example of the tension. You apply a tensile force on the component, uniaxial load. You are stretching the component, thereby the material undergoes an increase in length and then a reduction in cross-sectional area. Okay, so the final length is equal to initial length plus it undergoes some increase in length, that is extension. So the final length comprises of the initial length as well as the increase in length. So that constitutes the final length, and the cross-sectional area undergoes a small reduction in the area because the material has increased in length, thereby correspondingly the cross-sectional area is decreased. Then the second important type of loading is compression. Compression is opposite to that of tension. So the same cylindrical rod, if you consider of length, initial length is L0. L0 corresponds to the initial length and A0 corresponds to the initial cross-section area. So when you compress that material, then the material will undergo a decrease in length and increase in cross-sectional area. This is A and this is the final length. Next comes is shear. Shear is you apply a shear force to the material, shear stress or shear force, where the material undergoes some amount of plastic deformation with respect to the shear force. So these three are the commonly encountered loads, external loads that a material experience during fabrication or during the application or during which the material it is in service. It is exposed to certain loads like tension, compression, etc. Now coming to the important mechanical properties like strength, hardness, stiffness and ductility. So in order to find out the mechanical properties, we conduct some experiments. How a material responds to various types of loads like tension, compression and shear. So these mechanical property test results, they are used by many regulatory agencies. Thereby these test results should be consistent, and they should be consistent as well as standardized. So one of the important tests that I would like to discuss in the introduction part of this module is the tension test. In order to find out the mechanical properties like the strength, stiffness, ductility, the test that is conducted is the tension test. How a material responds to uniaxial loading, tensile loading. So the properties can be assessed by means of a tension test. How a material responds to uniaxial loading. Next, before going into this tension test, I would like to explain a few things about certain material properties like ductility and brittleness. A material is said to be ductile if it undergoes some amount of plastic deformation during the application of load. After the removal of load, still the material does not undergo any shape change, then it is called permanent or plastic deformation. If the loads are very low enough, that means if the loads are less than the load required to cause a permanent shape change in the material, then the material will undergo elastic deformation. So the types of deformation that I am going to discuss now, before going into the tension test and properties from the tension test, is elastic deformation and plastic deformation, and one more type of deformation that is known as viscoelastic deformation. Elastic deformation. What is elastic deformation? When a load is applied on the material, the material will undergo small amount of deformation, but as soon as the load is removed, again the material come back to its original shape before the application of the load. So this is called elastic deformation. Elastic deformation is mainly important in certain applications like bridges, which only undergo small amount of elastic deformation. So elastic deformation means upon the release of load, the material regains back to its original shape. There is no permanent change in the shape. The material only deforms elastically upon the application of load. As soon as the load is removed, the material regains back its original shape prior to the application of load. This is known as elastic deformation. Second type of deformation is plastic deformation. Plastic deformation means when the loads are slightly greater than the loads causes the elastic deformation, then the material undergoes a permanent change in shape, which is permanent. Even after the removal of load, still the material cannot regain back to its original shape. Prior to the application of load, there is a shape change involving on the application of load and after the removal of load. So that is called permanent deformation or plastic deformation. So simply, plastic deformation is there is a permanent shape change in the material due to the application of load. Even after removal of load, the material cannot regain back to its original shape. So this is known as plastic deformation. Then coming to the another type of deformation that is known as viscoelasticity. Viscoelasticity is also a type of elastic deformation, but it is not linear type. It is non-linear type of elastic deformation, as well as it is time-dependent deformation. The elastic deformation that we have discussed earlier, it is time-independent deformation, whereas viscoelastic behavior or viscoelasticity, which is seen in many of the polymeric type materials, polymers, as well as to a lesser extent over a certain temperature range to some of the crystalline materials. That means it is time dependent deformation. Upon the application of load, the material undergoes elastic deformation, which is not linear, as well as upon the removal of load, the material cannot completely regain back to its original shape instantaneously, but the elastic strain recovers over a period of time. The strain recovers with time, which is known as inelasticity. Okay. So briefly, once again, I discussed about elastic behavior of materials, elasticity, plastic deformation, and viscoelasticity. Elasticity is simply on the application of load, the material deforms elastically, and upon removal of load, again it regains back to its original shape as soon as the load is removed. That is elastic deformation. These are time independent deformations. These are time independent. They have nothing to do with time. Whereas viscoelasticity is time dependent elastic deformation. Time dependent elastic deformation. Plastic deformation is upon the application of load, the material deforms, undergoes plastic deformation, undergoes some extent of shape change. Upon the removal of load, the material do not come back to its original shape. It remains, the shape change remains even after the removal of the load. So that is plastic deformation. Whereas viscoelasticity, which is seen in many of the polymeric materials as well as in crystalline materials also, it is found to a limited extent over a temperature range, is viscoelasticity, which is time dependent elastic deformation. The material do not regain its original shape after the removal of external load instantaneously, but it recovers with time. Time dependent elastic deformation, that is known as an elasticity. So how the stress versus strain curve looks for an elastic material. The stress versus strain curve is simply linear in the elastic region. Stress is denoted by the symbol sigma and strain is denoted by the symbol epsilon. So before discussing this elastic behavior, I just explain about what you mean by stress and what is strain. Stress is load applied over the cross-sectional area. Stress is equal to load applied or force applied over the cross-sectional area, A naught, initial cross-sectional area. That corresponds to the stress. Whereas strain corresponds to change in length to the original length. So upon the application of load in the plastic deformation, the materials undergoes some amount of change in length. If it is tensile, the material undergoes increase in length. If the force or the load is compressive, it undergoes a decrease in length. So the change in length over the initial length is the strain. And the stress is the average stress. The stress, what we normally talk about, is load over which the load over the cross-sectional area, over the cross-sectional area over which the load occurs, is the average stress, because all materials, they are not homogeneous. Materials are polycrystalline. They may have number of grains. Material may have different phases. It may not be a single phase material. You may have two phase materials. So because of this inhomogeneities, the stress is not uniform throughout that material. So the stress is average stress. So average stress is load by the cross-sectional area over which the load acts. For example, if it is a cylinder, if a tensile load, this is a cylinder of cross-sectional area A naught and length L naught, the tensile load is applied, uniaxial tensile load is applied to this component, then stress is simply the load divided by the cross-sectional area, this cross-sectional area, the hatched region A naught. That is simply pi d square by 4. Okay. So this is stress and strain. So stress versus strain for an elastic, linear elastic material is simply, this is how you load that material. This indicates that you are loading that material within the elastic region, and then upon unloading, the material it follows the same path. The stress strain curve follows the same path. So this is known as linear elasticity or linear elastic material, linear elasticity. Upon application of load and upon unloading, its stress strain curve follows the same path. So this is linear elasticity. So it is time independent. As soon as the load is removed, the material regains back to its original shape prior to the application of load. Second type is plastic deformation. The material will undergo some amount of strain or some amount of deformation. Even after removal of the load, it cannot come back to its original shape, that is plastic deformation. And viscoelasticity, which is time dependent elastic deformation, that is stress versus strain curve for a viscoelastic material. So this is the path the material is loaded, and this is the path the material is unloaded. So the material do not follow, or the stress strain curve do not follow the same path when it is unloaded. Whereas in the case of linear elastic material, the stress strain curve follows the same path upon loading and unloading. Whereas in the case of viscoelastic material, the stress strain curve do not follow the same path after it is unloaded. And moreover, the strain does not recover instantaneously. It recovers with time. So that is known as an elastic behavior. Initially, the material undergoes some amount of linear elastic strain. Then the strain follows some asymptotic value. It reaches to about some strain of about some asymptotic value, and then upon unloading it follows a different path. And the strain, elastic strain, whatever the linear elastic strain initially the material experiences, it recovers upon the removal of load instantaneously, and whereas the viscoelastic strain that recovers very sluggishly with time. So this is an example of this stress strain curve for a viscoelastic material, or this is known as viscoelasticity. So linear elasticity, which load and unloading path follows the same path, loading and unloading path follows the same path. You have one more example for elastomers, which are time independent, similarly like linear elasticity, but elasticity is not linear, it is non-linear elasticity. So initially the stress strain curve follows a linear elastic strain, and then it follows a non-linear path, non-linear elasticity. So this is the application of load, and this is upon unloading. So this is also an example of non-linear elasticity, but it is time independent, similarly like linear elasticity. So the example for this non-linear elasticity is rubber. Example is rubber. For non-linear elastic material is rubber. But both linear elasticity and non-linear elasticity, these two are time independent. The recovered strain do not depend upon time. It is completely time independent. Whereas the one example of non-linear elasticity is viscoelasticity. This is time dependent. Okay. So let us now briefly go through these three types: elasticity, plasticity, and viscoelasticity. In elasticity, you have two types. One is linear elasticity and non-linear elasticity. So both linear elasticity and some materials which undergo non-linear elasticity, they are time independent. But one more example of non-linear elasticity is viscoelasticity, which is time dependent. So linear elasticity is the material do not undergo any permanent change upon removal of load. Again, it regains back to its original shape, and the stress strain curve follows the same path for loading and unloading. This is linear elasticity. Non-linear elasticity, which is also time independent. That is, example, some materials which show this type of behavior are elastomers. Example, rubber. The stress strain curve is non-linear, but it is time independent. Similar example of non-linear elasticity is viscoelasticity. This is time dependent elasticity. Initially, the material undergoes a small amount of linear elastic strain, and then with increase in stress, it undergoes some asymptotic value of strain, and then upon unloading, it do not follow the same path. It follows a different path, and this amount of strain is recovered, viscoelastic strain is recovered sluggishly. With respect to time, the strain recovers. So this is known as viscoelasticity. So these are the three types of deformations which we have discussed: elastic, plastic, and viscoelasticity. So we have discussed about elasticity, plastic deformation, and viscoelasticity. So linear elastic materials which undergo only, so far we have discussed about elasticity, plastic deformation, and viscoelasticity. So linear elasticity is the stress strain curve follows the same path upon loading and unloading, and it is time independent elastic deformation. Non-linear elasticity, which has two types, that is time dependent as well as time independent. So in the case of time independent, examples are elastomers, that is rubbers, so which show a non-linear elastic behavior. Whereas in the case of another example of non-linear elasticity is viscoelastic materials, which are seen by most of the polymeric materials as well as some polycrystalline materials to a limited extent or to a lesser extent over a certain temperature range. The loading and unloading path do not follow the same path, as well as there is some time dependent strain. That means the strain recovers after the removal of load with respect to time. So this viscoelasticity is an example of non-linear elasticity, as well as it is time dependent, whereas linear elasticity, and one more example of non-linear elasticity which is time independent, which is seen by rubbers, and non-linear elasticity which is time dependent is viscoelasticity. Okay. So with this, we just come to a brief introduction about what is plasticity, elasticity. Now in the introduction, I have discussed something about the ductile and brittle materials. A material is said to be ductile if it undergoes some amount of plastic deformation, permanent deformation before fracture. If a material do not undergo any amount of or very small amount on a microscopic scale, small amount of permanent deformation, and then it fractures, it is called a brittle material. So normally brittle materials do not undergo plastic deformation. So upon increase in load, they simply fracture before undergoing some gross amount of plastic deformation. Whereas ductile materials, they undergo some amount of plastic deformation before fracture. example of a brittle material is like chalk piece. Chalk piece, when you apply some stress or if you force it, the chalk piece breaks without undergoing some amount of plastic deformation. If you take a small steel wire and if you try to fracture it, so before fracture the material undergoes some amount of plastic deformation, that is, it pin downs before it breaks into two pieces or before it fractures. It undergoes some amount of plastic deformation. Now you have understood what is stress. Stress is load divided by the cross-sectional area over which it acts. If this is a material and a load is applied on this material, stress is load divided by the cross-sectional area over which it acts, and the strain is change in length to the original length. For example, in the case of an tensile loaded material, if the force is tensile force applied on a cylindrical rod, then the strain is change in length. Change in length means initial length is L0 and final length is L. This corresponds to L0 plus delta L. So change in length is initial length minus final length by initial length. Initial length minus final length by initial length is strain, that is equal to delta L by L0. So in the case of material which is loaded under tension, the material increases in length, and in the case of a compression, the material decreases in length. So strain is change in length to the initial length. So this strain is a dimensionless quantity. It do not have any dimensions because the increase in the change in length the material has undergone due to the application of this tensile load as well as the initial length, both have the same dimensions. So strain is a dimensionless quantity, whereas stress is load divided by the original cross-sectional area. So load, if it is in kgs or kilonewtons, divided by cross-sectional area, mm square, or kilonewtons. If it is force, you have kilonewtons per mm square. So stress is load divided by the cross-sectional area over which it acts, and strain is change in length to original length. And the important test that I have mentioned earlier is the tension test, uniaxial tension test. So how a material responds to uniaxial tensile loading, it is carried out by means of a tension test from which the important mechanical properties like the strength, ductility and stiffness can be determined. So in the case of a tension test, a material is loaded uniaxially by means of a tensile load, and this load can be calculated by means of a load cell which is calibrated, and the change in length upon the application of load is determined by a device known as extensometer. So knowing the change in length, the applied load and the material cross-sectional area, that is the geometry of the material, its original length, its original cross-sectional area, you can find out the stress and strain. So knowing the material geometry and what is the load applied and what is the extension of the material, what is the increase in length upon the application of load, stress and strain can be determined. Stress is the load by the original cross-sectional area, and strain is what is the change in length to the original length. Okay? So from that you can draw a stress versus strain curve for that material, and important properties like the stiffness, yield strength, ultimate tensile strength, and elongation, all these can be determined from the stress versus strain curve. Okay? So upon the conduction of tension test, a plot of stress versus strain is drawn. Stress versus strain is drawn because we know the geometry of the material, we know the load that is applied, load or force that is applied on the material, as well as what is the extension that is taking place, which is measured by means of an extensometer. So knowing all these things, you can find out stress versus strain, and then you can plot it stress versus strain. So the graph for a material, ductile material, it somewhat looked like this. So initially the material undergoes elastic deformation. As we have discussed, when the loads are low, the material undergoes elastic deformation, and when the load is greater than the loads causing this elastic deformation, the material will undergo permanent shape change, permanent change in the shape, permanent deformation or plastic deformation, and finally if the loads are still higher, then the material will fracture. So you are increasing the load at a fixed rate by means of a load cell, as well as you are finding out the extension upon the application of load, or what is the change in length the material is undergoing by means of an extensometer. And the geometry of the material is known. From that, calculate stress versus strain and plot it, where the graph somewhat looks like this. Okay. So this initial linear portion is up to the point A, which indicates, the point A indicates elastic limit. Elastic limit. It means the maximum load that the material withstands before undergoing permanent shape change or permanent deformation. So below which the material will undergo only elastic deformation. This is the limit of elasticity. Point A is the limit of elasticity. Below this point, A prime is proportional limit. Proportional limit, which indicates a slight deviation from linearity. Proportional limit indicates a slight deviation from linearity. So within this proportional limit, stress is directly proportional to strain, that is known as Hooke's law. Stress is directly proportional to strain. Stress is equal to E, capital E, into strain. So stress is equal to a proportional constant, proportionality constant into strain. This constant is known as Young's modulus or modulus of elasticity. This is an important parameter that can be found out from the tension test. Young's modulus, this constant of proportionality is known as Young's modulus, or this is known as Young's modulus or modulus of elasticity, elastic modulus. So point A prime is known as the proportional limit, which indicates above which the straight line, this line deviates from linearity. So within this proportional limit, stress is directly proportional to strain given by a scientist, Hooke. So it is named after him, Hooke's law. Okay, so Hooke's law, it states that stress is directly proportional to strain, where E is a constant, proportionality constant, very important parameter that is known as Young's modulus or modulus of elasticity. So this E can be found out from the slope of this straight line. So below the point A prime, the slope gives the constant, that is the Young's modulus or modulus of elasticity. The importance of this constant, Young's modulus, is from E, it indicates the resistance of a material to elastic deformation, or in other words you can say it indicates the stiffness or rigidness of the material. Resistance of a material to elastic deformation is stiffness or rigidity of the material. How rigid or how stiff the material is, it depends upon the parameter Young's modulus. Higher is the Young's modulus for a material, it means that it is more resistance to elastic deformation. Lower the Young's modulus, it is less resistance to elastic deformation. And point A corresponds to the elastic limit, the maximum limit or the maximum stress the material withstands before the material withstands without undergoing any shape change, beyond which the material will undergo a permanent change in shape. But below the point A, the material does not undergo any permanent change in shape. So that is point A, that is known as the elastic limit or the limit for the elasticity. Maximum stress the material withstands without undergoing plastic deformation, beyond which you have an important parameter, strength parameter, that is known as sigma subscript y, which indicates yield stress. Yield stress. So this indicates above which the material undergoes plastic deformation. So this yield stress can be found out by drawing a line parallel to the initial portion, initial linear portion of this curve at a point of 0.002 strain, or can also be said as at a point of 0.2% strain. A line is drawn, an offset is drawn parallel to initial linear portion. Where this line cuts the curve, it indicates where the line cuts this curve indicates yield stress. Okay, so yield stress is at a value of or at a point of 0.2% or 0.002 strain, a line drawn parallel to initial linear portion. So as this curve deviates from linearity beyond the proportional limit, this straight line which is drawn at 0.2% strain, it cuts or intersects the curve at some point of stress. So that stress is known as yield stress. So at this value of stress, the material has undergone a permanent strain of about 0.2% or 0.002 strain at a value of stress equal to yield stress, that is sigma y. Beyond which, beyond this yield stress, the material undergoes strain hardening. Strain hardening means stress required to cause further deformation increases with increase in stress. Strain hardening or work hardening means stress required to cause further strain will increase with increase in stress. That means you require more amount of stress to cause further strain. Okay, as strain is increasing, the stress has to increase up to a certain point, maximum in the curve. So this point is known as ultimate tensile strength. So this is maximum, this point is maximum in the curve, which indicates that the material can withstand a maximum load without undergoing failure, without undergoing fracture, or the material undergoes a uniform amount of strain, up to this point, which is indicated by the maxima in the curve, that is ultimate tensile strength. So up to this point, the material will undergo uniform strain, and the maximum load the material can withstand with respect to this uniform strain, beyond which the stress required to cause further strain drops down, and the material from the point of ultimate tensile stress, it undergoes localized reduction in area, which is known as necking, or in other words, you can say as the material will undergo non-uniform elongation. So this is the total elongation. The total elongation the material has undergone, which includes this uniform elongation, and beyond this ultimate tensile strength, the material will undergo non-uniform elongation. Okay, uniform elongation means if this is the material of cross-sectional area A0 and length L0, upon application of this tensile force, the material will undergo uniform strain. The material increases in length and reduction in cross-sectional area occurs uniformly. So that is uniform elongation up to the point of ultimate tensile strength, or the maxima in the curve. Beyond this ultimate tensile strength, the material will undergo non-uniform elongation. So that is known as localized reduction in cross-sectional area. The material does not undergo uniform elongation. At some location, the material undergoes heavy amount or high amount of plastic deformation when compared to the other part of the component. So this localized reduction in cross-sectional area is known as necking. Necking, that is known as localized reduction in cross-sectional area. So this occurs beyond the point of ultimate tensile strength. The onset of necking or the starting of necking occurs at point of ultimate tensile strength, and further the material undergoes fracture, beyond which, with increase with the stress, the material undergoes fracture. So this indicates fracture. So from this stress strain curve, the important parameters that can be determined are the strength and ductility, and the important parameter within the proportionality limit, the slope of the straight line gives the Young's modulus. Ductility means what is the total amount of strain the material has undergone, what is the total amount of change in length, what is the increase in length, and what is the corresponding reduction in area the material has undergone. That gives the ductility of the material. More is the increase in length, smaller is the reduction in the diameter or reduction in cross-sectional area, more is the ductile material. Whereas strength parameters are yield strength and ultimate tensile strength. So these two are the strength parameters, and ductility is measured by increase in length, that is the percentage elongation. What is the amount of elongation the material has undergone with respect to the load, and what is the reduction in cross-section area. So these are the main two important parameters, strength and ductility, that can be measured from this tension test. As well as within the elastic limit, another important property is Young's modulus, which means resistance to elastic deformation. So initially I made a small mistake. Please do correct it. For any clarifications or for any doubts, you can mail me to my mail ID vijaya.511@gmail.com, and my mobile number, I have missed a number, 9052003346. Kindly correct my mobile number, 9052003346. For any clarifications, you can mail me or you can contact me.